Hello, in this screencast we're going to discuss briefly the overall picture of what's taking place in chapters 6 and 7 in our text, and also walk you through using the computational formulas for finding the correlation coefficient, the least squares regression line, and the standard error of estimate. I'm using a problem that was in the book as one of the textbook examples. Although it is all spelled out step by step for you on table 6.3 and 7.1 and 7.3 in the text, I think it's helpful if you kind of see it written out also, and let's just talk through this together. So this was an example or a scenario where there were 5 individuals selected, and the hypothetical context was the fact that we were taking a look to see if there was a relationship between the number of holiday cards an individual sent and the number of cards that they received. And this was an example here where there were 5 sets of data, 5 pairs. You got 13 and 14 as one, 9 and 18 as the other, and so on. And we wanted to see if there's a relationship between these two values. For example, could the number of holiday cards sent by an individual help predict the number of cards that they will receive? So first thing we want to do for any of these is actually set up an XY scatter plot. So that's what we have over here on the right. The X values are along the horizontal axis and the Y values are along the vertical axis. So this represents the number of holiday cards they sent versus the number that they received. And I plotted these values here one at a time on this chart. So for example, 13, 14 is represented right here at this point. So the 5 coordinates were graphed, and you can see that there is somewhat of a trend as from the scatter here. It seems to be increasing, and if you recall, dealing with correlation coefficients, we're taking a look at 2 things. First off, is it positive or negative? And is it strong or weak? And in this case here, we can see that it's certainly in a positive direction. As one value increases, so does the other one tend to increase. But now we're going to take a look at identifying just how strong that is through the correlation coefficient. So the computational formula for this is in the text, and it's represented right here. And these variables here stand for the SP sub xy stands for the sum of products, and in the denominator underneath the radical here we have the sum of squares for x and the sum of squares for y. Now these 3 values we need to get by walking through these 3 formulas right here one at a time. Now what I tend to do for any of these is set up my X and Y tables, and then I go across the top, and I know from these formulas I'm going to need the sum of the X squared. So I'm going to have a column here of my X values squared, and then I'm going to have a column of my Y values squared, and then I'm going to have a column of my X value times my Y value. So these values in these 3 columns are taken from each of these little formulas from these coordinates over here. So for example, the X squared, for each one of these 5 values, I took this value under the X column and squared them, multiplied it by itself. So 13 times 13 is 169, and so on. For Y squared, I took the Y values and squared them, and for the XY column, I multiplied the X times the Y. So that's where those 5 values come from. In these formulas, you'll see that the sigma symbol is used quite often. And sigma represents, again, summation, or the sum of those values. So along the bottom of this table, I set up a row where it's the sum, sigma, of each of these columns. So 35 represents the sum of these 5 values, and 60 represents the sum of these 5, and so on. I also have n here, which is the sample size. There are 5 pairs of values. That's my n. And then later on in the formula, we're going to need actually the mean of the x's and the mean of the y's. So I took care of that here. The mean of the x's is the sum of the x's divided by the n. So 35 divided by 5 gives me 7. And the mean of the y's is 12. So then I take a look at this formula. I realize I need these three values. These three values are from these three computational formulas found in the book. And I'm going to walk through them one at a time. For the sum of the x's squared, now remember now there's a big difference between this and this. This means I am adding up all of the x squared values. So the x squared, each one of these, they add up to 325, and that's the value here. This represents the square of the sums of the x's. So I have to find the sum of the x's first, which is 35, and then square that value. I take my time and plug them in one at a time, and in this case here I ended up getting a value of 80. That's for the sum of the squares of the x's. Now I have to do the same thing for the y's. And then this formula is represented by, and again this is the sum of the products. It is the sum of the x times y, which is the sum of this column, minus the sum of the x's, which was 35, times the sum of the y's, which was 60, divided by the sample size, which is 5. I take my time here. Use the calculator step by step so that I don't make an error. Subtract 484 from that value and I can get a value of 64. So each of these three values represent the input needed to find my R. So I'm going to take that formula, substitute those values one at a time. And again, here's another area where you might want to take your time finding the square root of 80 times 80. And then the 64 divided by this denominator is the final value of 0.8, which is my correlation coefficient, or R. And as you can see, it is positive. We predicted over here from looking at the scatter that this was going to be a positive correlation. So 0.8 is positive. And it is closer to 1 than it is 0. So it's a fairly strong correlation. Now, that's how to find correlation coefficient, or my R value. Now we're going to walk through what's called the least squares regression line. And the value of this formula is pretty large moving forward in this area of statistics. As you can see, we have 5 different data points plotted on this XY scatter. And what we want to do is use these 5 values to help predict future values. So for example, if I selected another individual at random and they ended up having, for example, 6 holiday cards that they sent out, or an X value of 6, I want to predict what their Y value is going to be based on these other 5 data points. So I can look over here and see that, all right, if I want to predict what 6 is going to be, I can plug it in here somewhere and get an idea, or we're going to use statistics to find out what is the equation or formula for what's called the line of best fit. So this line here we're graphing. Again, you can do it by hand and judge it with your intuition, but we're going to use this formula here. And I'll walk through this. So y prime stands for the predicted value of y. We need to come up with a formula here where we can plug in our x value that we're predicting. I used the example of if we had a 6th person here who sent out 6 holiday cards. I want to plug in a value of 6 and get a prediction for y. And on the surface, this formula looks nice and easy. We have y prime is equal to b times x plus a. But then down here we have 2 different sets of formulas to represent the b and the a. So the b is represented by r, which is the r that we had here from the chapter before, times the square root of the sum of the squares of y and the sum divided by the sum of the squares of x. So these 3 values I am getting from the 0.8 here, 80, and 80 from the problem before. Plug them into the formula, take my time, and I get a B value of 0.8. The A is represented by, and it's y bar minus b times x bar. Y bar and x bar are the means of our y's and x's. So if you recall, we had a mean of our y's was 12. The b we just found here, 0.8. And the x bar, which is the mean of our x's, was 7. So I plug those values in, and I get a value of 6.4. These two values are plugged into the b and the a of that formula to get this equation or function. And how this works is, if I want to take a prediction of, I have somebody who sent 6 holiday cards and I want to predict how many holiday cards they'd receive, I take the value of 6 and I plug it into this formula. And I get 0.8 times 6, and I add 6.4 to it. And that will give me a value very close to where this line is here, probably a little bit under 12. Then the last part is what's called the standard error of estimate. And what this means is this. We've now come up with a formula here of least squares regression line, which is a method for us to predict what the y value is going to be for any given x value. So for example, we wanted to predict an individual who had 6 holiday cards that they sent out. We want to predict how many holiday cards they would receive. We would use this formula and we would get a value. But the chances of that value being absolutely correct every time is very slim. Realistically, we're going to get a value close to it. You can't really expect to get exactly what that line is going to give us, but we're going to give us a value close. So there is a difference between the actual value for each of these and that predicted value. Just like we have a spread of values for our standard deviation back in the earlier chapters, here we have a spread of variation for each of these. And that's what's called the standard error of estimate. And this formula, represented by this pretty impressive looking thing, is the square root of the sum of the squares of the y times, and take your time with parentheses here, parentheses 1 minus r squared, divided by the sample size minus 2. So each of these values I am getting from everything I set up here on this page. So the sum of the squares of the y was 80. My r was 0.8. My sample size was 5. Take my time, plug those in. I'd recommend breaking these down one at a time. Like for example, you can see here that the 1 minus 0.8 squared, I took my time and did that separately and got 0.36. And then take my time and get a value here and take the square root. And that gives us what is called the standard error of estimate, which in this case here is approximately 3.10. In all, what that means is this. I have a set of data, 5 coordinates, that I'm going to plot on a scatter plot. I can see from these 5 points that there is a trend. There's a positive correlation between the two of them. This R value gives me a sense of exactly how strong that value is. In this case here it was 0.8. The closer that value gets to 1, the closer I know that this is a very, very strong correlation. This least squares regression line is the actual calculation we're going to use to make our prediction. If we had, for example, an additional member who I used the example of sending out 6 holiday cards, I can look at the scatter and make a prediction that's around here. Now I'm going to use this formula, plug in 6 and get an estimate right around here. But I can understand that this is most likely not exactly correct. So 3 gives me an idea about, on average, how far that prediction will be from the actual case. Hope this helped walking you through those.